Okay, so in the lecture today, we are going to discuss intrinsic representations for 3D shapes. In particular, we're going to discuss neural networks for point clouds and for meshes. So we're going to discuss neural point clouds and deep meshes. And first, we are going to give an overview of the kind of representations we are dealing with point clouds and the different architectures for point clouds. And then we are going to discuss meshes, and using the background that we discussed 3 lectures ago on characteristics of meshes, we are going to discuss how to build a network, general network for meshes. And the representations will be by a graph. And so in the first case, point clouds are point sets of elements. And then in the second, the neural network has to deal with a graph, because a mesh is a graph, and be a graph neural network. So the architecture here, the first for point clouds, we have a neural network for point sets, for sets of elements. And in the second, we have a neural network for graphs, but take into account the characteristics of these objects, because they are representing 3D shapes. Okay, in the first part, I'm going to use this tutorial that was given by Leo Gibas at SIGGRAPH 2019, entitled Deep Learning for Point Cloud Data. And this is a very good summary of the state of the art at the time for point clouds with neural networks. Okay, so a point cloud is a very common 3D representation and have 2 important characteristics. First, point clouds are very close to sensor data. You have different types of sensing devices that directly capture a point cloud. And also, point clouds are very simple in terms of as a representation, because we can both convert to and from a point cloud and other shape descriptions, such as surface mesh, 3D grids, or implicit shape, or a depth map. So here we see some examples of point clouds. This is point cloud generated by LiDAR sensor. This is a point cloud generated by a depth camera. And here is a point cloud that was generated by structure from motion, such as CoMap that we saw in previous lectures. So before this introduction of neural networks for point clouds were used in 3D deep learning in other architectures, such as the ones that we saw in the previous lectures. Basically, the point clouds were converted to regular representations, such as a 3D grid, a voxel grid, and then they were processed by a grid network that uses 3D convolution. This has some qualities to use convolution, but has some problems, like the 3D convolution has a complexity that's all of n cubed and takes a lot of space. And at the same time, when you convert geometry such as a point cloud to a voxel grid, we have quantization errors. So this motivates the need for neural network for point clouds. And also, we can use other types of neural networks, such as implicit neural networks, as we see in the previous lectures, to create a representation from point clouds. And so we can use point clouds to generate images, and then use multi-view images to create implicit models and process and do 3D reconstruction from that. That we saw this in the previous lecture. But in this case, also we have like this intermediate step to generate the images, and we don't take advantage of the characteristics of point clouds that directly are captured by devices. So we don't need to do this intermediate step to generate an image. We have already a point cloud. So this poses the following question. So can we create a neural network that do feature learning directly from point clouds? And the answer for that is yes. This is with point set neural networks. And so in this first part of the lecture, I'm going to present this two neural networks, two architectures, the PointNet and PointNet++. This is an evolution of PointNet that are very effective to process point clouds, and both for applications such as point cloud analysis and point cloud synthesis. And this is a seminal work that was developed by Léo Gibas at Stanford, that actually is the author of this tutorial. And so what's the PointNet architecture? So the PointNet architecture does end-to-end learning from irregular point data. And as such, is a unified framework for various tasks, such as classification, segmentation, both segmentation of parts and semantic segmentation, and also for shape synthesis apart from single images. And so it's a unified framework that uses a very simple data structure, just a set of points. But there's a challenge, because the challenge is that the model for the neural network has to respect the key property of point clouds. So basically, there are two main properties that need to be respected. And we have to develop a neural network, an architecture that preserves some invariances that are inherent to this type of data. The first one is a permutation invariance, and the other is transformation invariance. In terms of the permutation invariant, we notice that a point cloud is a set of unordered points. And then we need to have a neural network that's invariant to this property, because the input of the neural network is an unordered set of points. And if you do any kind of permutation of these points with a different input, we should get the same results, because they're the same set of points. Just changing the order doesn't change the nature of the data. And so we need an invariant network that's going to be invariant to this any factorial permutations of the elements of the set of the 3D points. And so how we do that? The idea is that you create permutation invariants using a symmetric function. So a symmetric function is a function that is going to permutate the elements, the points that are the input of the neural network, and that's going to be processed by the neural network. So here we have like this pi permutation, and then if I have a function f of a set of elements, and I do a permutation, I would like to get the same result. And then some examples of asymmetric functions that are invariant by permutations are, for example, the max functions or a sum. And so the question is, how can we construct a universal family of symmetric functions to be used with a neural network, such as this? The idea is the two ways to incorporate this into a neural network. The simplest way is just to use some aggregate function of all points that is a symmetric operator, like max. So here we are aggregating all the elements, taking the maximum, and then this is a symmetric function. And as another example would be to sum all the elements. And in this sense, that this simple form of using this symmetric operator G basically discovers aggregate properties of the geometry, such as the stream or the sum or things like that, right? But this is effective, but it's not completely powerful. Can do more when doing deep learning with a neural network. The more sophisticated way to exploit this permutation variance within a neural network is to embed the points in a high-dimensional space before the aggregation. So we aggregate the elements with some embedding function into a high-dimensional space that encodes other interesting properties of the object. And so just learning this embedding function is an important characteristic of the neural network that's particular to machine learning. And then to preserve the permutation variance, we have this symmetric function. And then we can have any kind of neural network here to extract properties. And so this is the base of the point-net neural network, because it's a composition of an embedding H with a symmetric function G and a neural network gamma. And then has an output here of the analysis of this point set. And so if this G is symmetric and the other elements are neural networks, and then the entire result of this network will be invariant for operations of permutation, and the network will inherit the property of this symmetric function. So this is what we call the point-net vanilla. It's the basis for processing point sets and preserving invariance under permutation. So the second invariance that we need is a transformation invariance, because we have 3D points that are in space, and if we do any rigid motion to this 3D point, solve them, they are still the same geometry, they represent the same geometry, and this is similar to translation invariance that we discussed in terms of images. So the point cloud should not alter its characteristics by rigid motions. And so this shouldn't change any result of the neural network, such as classification and other types of analysis. So we have to incorporate transformation invariance in the network. So one way to do this is to do alignment of the points. So we do alignment of the inputs, and then we keep this point set aligned to some frame of reference. So we do this with transform network. So this transform network is going to take the input point cloud and create a transformation, a global transformation, that's going to align all the points and create the parameters of this transformation. And then we are going to work with this transformed point cloud that's going to be in the same transformation framework and going to be invariant by transformations. And so the good thing is that the transformation is just a matrix multiplication. And then the transformation network computes this parameter, computes this matrix, and then the network is going to multiply all the points by this matrix. And then we have the points alignment, and we have guaranteed the transformation invariance. And so this third element of the point-net network is this embedding space alignment that takes this transformation network and combines this with embeddings. So we have like the first layers of the network Then we can have embeddings, such as we discussed, related to the permutation variance. And then we can apply this transformation to the point embeddings in the same way. And then this can be propagated to the layers of the neural network. And for that, to do this alignment, this transformation is learned by the neural network. And here we use regularization loss so that the transformation matrix is very close to an orthogonal matrix. And so it's going to be close to a rigid motion of the data. And then that is going to basically set a frame of reference for each stage of the process. And so this, combining all these elements, we have the first architecture for a point net. So this is a point net for classification. And here you see we have the input points. And then we have like this initially input transform to align the points. And then we have embeddings and other feature transforms, and keep doing that until the end. And in the end, we have like an aggregate function that's going to be a symmetric function. And then it's going to compute like a global feature that's going to be used here for classification. So this is a point net for classification. Then we can extend the point net base to do also segmentation. So when we do segmentation, we take that initial part of the point net without the classification. And then we take this last local embedding and the global feature. And then here we put this into this branch that's a segmentation network. And then here we have, this is n by 64, and then is 1024. And then we have here like n times 1088. So this, we do this for each class that we are going to generate as a global feature. And then as we do this, we incorporate these point features and process to have the scores for the segmentation of the points that is going to be based on the classes of that are generated by these global features. And so here we can see like some results for segmentation objects. And here we're segmenting the object in different parts. And notice that we can segment complete point sets, such as those, a knife, a bag, a cap, or incomplete inputs, like partial inputs. And just seeing part of the points, it can segment the parts very faithfully. Like in the case of this mug, there's many parts missing on the case of the table, and it still is able to segment the top of the table, the legs of the table. So it's very powerful, this kind of analysis. And here is results on real data. So this is like a data that was generated for 3D scans from Matterport directly with LiDAR and depth cameras. And yes, it's incorporated with the points with color. And this is the semantic segmentation of the scene. So you see like there's a room, have the table, the chairs, the blackboard, and the lamps, and the network is able to do a segmentation with that. And it's not a problem that like some points are missing because the network is powerful to learn, the characteristics of the data because of the architecture respects the nature of the data and the invariance of the point sets. And as a result, we can see first that the point net is very lightweight compared to what we have seen in the previous lecture. Like for there's volumetric neural networks and multi-view neural networks, 3D voxel grids and multi-view. It has a rate of like 80% of memory saving compared to volumetric, and much more for multi-view. And also it's very fast if you compare the point net with a volumetric or multi-view. We have savings of 88% in terms of floating point operations. And so that means that a point net architecture is a very promising architecture for portable devices because it doesn't require a lot of computational power, and also doesn't need a lot of memory. And so in that sense, it's important architecture for applications that use this mobile devices and computation. And one of the characteristics of the point net that's very remarkable is that point net is very robust to that data corruption. So this graph shows that if we drop 50% of the data or change in some ways, it's going to just lose 2% of accuracy. So here is a VoxNet, that's a voxel grid network, and here is the point net. And you see that practically maintains the accuracy up to 50% of the data, and then starts decreasing obviously. But the VoxNet decreases linearly. So this is also an important point, and it raises a question: why the point net is so robust to missing data? And the reason is that because it concentrates on points, and the points are unordered, and concentrates on the important points, basically gives attention to the important points of the shape. So we call like these critical points. So this is the input of the neural network, the point set and colored by some characteristics. And here we see the points that are concentrated in terms of the processing and analysis by the point net neural network. So basically, it picks up the interesting points in terms of perception and the structure of the shape. And that's the reason, because you can drop redundant points, and the network is going to concentrate on the important points. And that gives a very good robustness in terms of that data corruption. But the point net is not perfect, and it can be improved. And so the authors of point net, they created a point net plus plus, this improved version of point net, and is an improved version that addresses some limitations of the point net that we're going to see here. So point net had many advantages between voxel grids that use convolution, and some disadvantages, because if you see here, like a voxel grid based on neural network that uses a 3D CNN, uses 3D convolutions, creates a representation that is multiple levels of abstractions in terms of analyzing the data. So creates a hierarchical feature structure that learns features at different semantic level. And that's very powerful, and is a characteristics of the 3D, the convolution operator, in that case for voxel grids, a 3D structure of the shape. But the point net, because of using this aggregation, process does embedding and aggregation. And so in that sense, it cannot do this hierarchical feature learning. It's only do a global feature learning or individual points feature learning. So this is the structure of the point net vanilla, because here we see like the embeddings, and if we, in the end, we can use the aggregation to do a global feature learning. But we don't have like this hierarchy, and we don't have local properties at different resolutions. And so the idea is to address that, and because the point net vanilla doesn't use local context, just global context, and have a limited local invariance because it's dealing with all the points at the same time. So how we extend point net to address these issues and have the same properties of the convolutional neural network. So the basic idea is to apply point net recursively to local regions. And with that, we have, on one hand, a hierarchical feature learning, we have a local translation invariance, and we will maintain a permutation invariance, which is essential to process points. And so now we're going to see how that was developed based on this idea. So the idea is this hierarchical point feature learning, and we start with the same setting of the point net vanilla. So we have any points in space here, or just see this in 2D, but the point net is in 3D. And then we have all the points. But if we want to kind of look at the local neighborhoods, we select one point and look at the points around it, right? And then, so instead of having any points in the global space, we are going to have k points in a local coordinate space, like this UV frame. And that defines the locality that we're going to exploit to do hierarchical point feature learning. So the idea is to apply point net to a local region. And then we have the benefit of point nets for analysis, but we have the localization using selecting that region. But how do you select the region? The idea is that in here we can also do this embedding and have like a high dimensional feature space associated with this small region. And then we can, after selecting this point and that region, we pick other points and other regions that sort of like complement the whole shape. So we look for a point that's outside this radius of this influence of this region, and then create another region and keep doing this and creating other points of reference that distributes around the domain. And in the end, we cover the domain by these local areas, and we can do like a set abstractions. Basically, we combine this farthest point sampling from the region with grouping to create the region to be processed, and apply point net to the points within each region. And so this is basically the architecture for point net for classification and segmentation. Note that here we have this set abstraction that we do like sampling and grouping, and then apply point nets to the results, and keep doing this. And at each layer here with set abstraction, we have a hierarchy of points, because we start the initial point set, and then we have these local regions that are going to be processed with features and so on and so. And so in the end of this hierarchical point set feature learning, you have the features And then from here, we have the point net as a whole. And then we can, for example, for classification, we use that with this feature vector to do a classification with a fully connected MLP, such as in the same for convolutional neural networks for images or for voxels. And so in that sense, we accomplished the task of maintaining all the advantages of point nets and addressing the limitations that point net vanilla didn't have. So point net plus is like the state of the art in terms of the neural networks for point sets, and can be used for classification and also for segmentation and synthesis, because here we are aggregating and do classification. But if we want to kind of do segmentation, we do the opposite of the abstraction here, because we take the features and then we expand them using interpolation and up convolution. And so we go from the hierarchical local regions backwards to the resolution of the initial point set. And in that sense, we can segment in the same way we could do this for the point net vanilla, but take into advantage this more powerful semantic abstraction of the hierarchical point set feature learning. But there is one thing that's important to discuss that we didn't discuss up to now, is that if you look at the pictures in this image and also the other pictures like here, we can see that the spacing between the points is very regular. And that is important if we are going to do like this hierarchy. And so, on the other hand, the sensing devices and other processes, they usually generate sampling that are non-uniformity. That's a density that varies across the domain. So this is common because of several effects like a perspective, radial density variation, motion. And so usually the input of a point set neural networks can have non-uniform density. And this is challenging if you are doing this local feature learning for the hierarchical point net plus. And we need to address this in some way. So you see here that compared a point net vanilla with point net plus, if the distribution of the points has a variable dense, so you have in this share, the seat has a density much higher than in the back and in the legs. And then if we kind of drop the number of points from 1024 to 128 and apply this for a hierarchical point net to do some classification or some other processing, as we change the number of the points, this has a huge impact. So up to this point here, the point net plus is better in terms of accuracy, but then the variable density starts to affect the point net plus and decays very rapidly, while the point net vanilla is much more robust because it's not so sensitive to these local regions. So we need to address this density variation, and this is the last part of the point net plus. So the idea to do robust learning under variable sampling density is to actually change this size of these local regions, not within just a hierarchy, but adaptively. So because before we had like these local regions applied recursively to each layer and each level of the hierarchy. But here, the idea is that we want to have another operator that would be like this multi-scale grouping or multi-resolution grouping that basically change the size of the neighborhood that's going to be analyzed depending on the number of points. So we keep neighborhoods with the same amount of points, change the radius. So here we have a lot of points in this small neighborhood. So for that, we need more. And then we can do this with this type of grouping. So, or multi-scale or concatenation. And there's different trade-offs, and both work nicely. And during the training, we can also use this input point dropout to augment this robust learning. And so with that completes the architecture of PointNet++, and it gives very, very good results. And so up to now, we discuss PointNet and PointNet++ for analysis tasks, such as classification, segmentation. Now we are going to discuss the PointNet for point cloud synthesis. And then the idea is to generate a 3D shape from a single image. So here we have like two images of a car and a bottle, and then we train the neural network in the supervision using appropriate labeled data sets with the point sets. And then for the inference, we give the image and generate the point sets correspondent. And it's a 3D point set. It generates the shape from the point of view of the camera that's taking the image, but from all the other points of view. So, because we learn with doing the supervised learning with the real 3D data, right? And so how that's done? Is a common theme that we are going to see here in the course. We have already seen part of it, but it's a theme that is the synthesize for learning. Basically, we use differential rendering to learn a shape in a sort of a self-supervising manner, right? So here we have a data set like this ShapeNet that we mentioned in the beginning of the course. And from this data set, we can render images of the elements of the data set. But we can also sample point sets from the models. And so we have like a training, self-supervising training that look at the images and the ground truth of 3D shape. And we have a neural network that's going to learn end-to-end to synthesize the 3D shape from single images. And so here, what was done, the training was like it took from ShapeNet 200,000 shapes with 2,000 categories and generates 10 million images with the ground truth point sets. And that was done to train the PointNet for synthesis with augmentation of a part that we are going to see now. And so the idea here is that we have a 3D model in the data set for this ShapeNet. And then we have this 3D model. From the 3D model, we can generate an image and also sample points. And these points are going to be a reference that the neural network has to predict. And we have to learn this, right? And then the idea of the structure of the network would be as such as a encoder-decoder or encoder predictor. So we have the image, we have an encoder that are going to create a shape embedding space and learn a predictor that's going to generate a point set that has to be the same as the one that is used as a ground truth. And we need a way to kind of compare this to point sets. And this is what is the important thing about the aspects of this architecture. And it's crucial that we have to for the network to learn in this fashion. It has to be able to compare the different point sets for doing the optimization of the neural network and learning the shape embedding. And then there are different ways to compare point sets. We are going to use like a distance metrics for point clouds. There are three main ones that you can consider. One is the Hausdorff distance, the other is the chamfer distance, and the other is the Earth mover distance. So the Hausdorff distance is classical in mathematics to compare shapes and sets. And the chamfer distance is very practical, and the Earth mover distance is more complex to compute and has some advantages. So the point net uses both the chamfer and Earth move, and the choice for the metric for this synthesis from point sets using the point net is the Earth movement. That's basically using optimal transport. But in many other applications for point sets, the chamfer distance is the choice because it's simpler and it's very effective. And so what is the chamfer distance? The chamfer distance is simple because basically it computes the reciprocal closest points for each point. So for each point in one set, looks for the closest point on the other set, and does this from the points of one set and the other set, and computes the minimum. And then this symmetric thing is the chamfer distance. And it's very intuitive and works very well and simple to compute. And we're going to use this further on in the lecture. And then there's one thing that we need to consider is that we want to synthesize a shape from an image. And then we want to learn shape structures. And we've seen in the first part for analysis that those embeddings would learn some structures. But now we want to learn the structures from relation between the image and the point sets. And for this, we are going to use a convolutional neural network that's going to inform the predictor. And we need to consider what kind of structures that we are going to try to understand during the learning process. And for that, it's important to consider the natural statistics of optical geometry. Because if you want to learn shape structure, there are two kinds of structures. One kind is like a smooth structures that, in general, the objects are piecewise smooth. And then so many parts of the object are smooth, and there is strong correlation among the points in those regions. So these are like a planar patches, like in this back of the chair, or cylindrical patches in the airplane. But there's also some sharp local features where there are discontinuities, like here in the tip of the airplane or in this corner. So there are points where you have variable geometry neighborhoods. So there are like characteristics that are critical points. And we need to consider both. And then what this extension of point net for synthesis developed is a two-branch architecture, like one branch to capture the characteristics, the statistics of smooth structures, and another branch to capture the features of this critical points. And so the first one is going to be a deconvolution branch, much in the sense the one that we saw for .NET++ to do segmentation. And the other one is going to be this a fully connected branch that's going to get the tails and the high variance parts. And so we have for the encoding, we are going to have this convolution neural network, and then the result is going to be fed into a deconvolution branch to capture a smooth structure, and into a fully connected branch to capture this detailed of the geometry. And the result of these two branches are going to be agglomerate using a set union, and this is going to be the result of this second part of the network. And so the deconvolution branch, basically what it does is a NAP convolution is going to expand the features, and in a way, it sort of generates a smooth coordinate map. And that means that geometrically it's going to do a smooth parametrization of the features. Like here, you can see that it's very smooth. On the other hand, this fully connected branch is going to detect the high variability patches, and then just highlights the important points. And so here we see how this combination is very effective. We are going to see the classification of the points that were detected by the convolution branch and the fully connected branch. And so the blue points come from the convolution branch, and the red points come from the fully connected branch. And you see that the red points are like this stream points with high variability. And then the blue points are these very smooth parts. And then this shows that this is the right idea to create architecture that takes into account the natural statistics of the shapes. And here are some examples of the result of the synthesis. And here we can see that this is a synthesis from the same view of this image. And here we see that the result of new views, and it's very effective even for like a simple object that is symmetric like this, and that detects the symmetry and everything, and objects that are not symmetric and are very different from different sides, and kind of learn very well both the symmetry and the detail. And here is the result from real images that are not necessarily was in the training. And then we have the input view. This is the synthesis from the observed view, and this is other angles. And you see that captures very well the geometry and constructs very well the geometry. And so this last row, these are images that are not within the training data. Okay, so now I'm going to stop for Q&A.